There's something awe-inspiring and deeply unsettling about staring up at the night sky and realizing just how little we truly understand. The universe is full of mysteries that refuse to fit neatly into our textbooks, phenomena so bizarre they make even the most seasoned astronomers pause. Think about it, we've mapped distant galaxies, unraveled the life cycles of stars, and even glimpsed the afterglow of the Big Bang itself. Yet, for every question we answer, the cosmos seems to throw another enigma our way. Strange signals pulse from the void, celestial objects move in ways that defy gravity's rules, and entire galaxies appear where they shouldn't. These aren't just minor gaps in our knowledge, they're cosmic puzzles that shake the very foundations of science. Take those eerie radio signals from deep space, for example, repeating bursts of energy so powerful they could cross billions of light years to reach us with no clear source. Or consider the galaxies that spin too fast, their stars clinging together as if held by invisible hands, forcing scientists to ask, is there something out there we can't see, or are the laws of physics themselves different in these distant corners of the universe? Even closer to home, our own solar system harbors its own oddities, like the strange, tumbling motion of some asteroids or the unexplained heat emanating from Jupiter's poles. Each of these mysteries is a reminder that space isn't just vast, it's profoundly, tantalizingly weird. What makes these cosmic riddles so captivating isn't just their strangeness, it's what they reveal about our place in the grand scheme of things. Every unexplained phenomenon is a clue, a breadcrumb leading us toward a deeper understanding of reality, and that's exactly what we're exploring today. From ghostly energy beams to structures so massive they challenge the limits of cosmic growth, we're counting down 25 of the most bewildering discoveries in modern astronomy. Some might hint at entirely new physics, while others could rewrite what we know about the universe's origins. So settle in, because this journey isn't just about listing oddities. It's about peering into the unknown and asking the biggest question of all: how much of the universe's story are we still missing? The answers, or lack thereof, might just leave you seeing the stars in a whole new light. One summer night in 1977, a radio telescope in Ohio picked up something extraordinary. A burst of radio waves so intense, so unnervingly precise, that the astronomer who discovered it scrawled, "Wow." Right there on the printout, that single word would become legendary. For 72 seconds, the signal blared from deep space, locked onto a frequency that scientists had long speculated might be used by extraterrestrial civilizations. And then, just as suddenly as it appeared, it vanished. No trace, no repeat, no explanation. Decades later, the WOW signal remains one of astronomy's greatest unsolved puzzles. What makes it so baffling isn't just its strength or its bizarrely narrow frequency, it's the fact that it checks so many boxes for an artificial signal while defying every attempt to pin down its source. Imagine tuning a radio and stumbling across a voice speaking your language in perfect clarity, only for it to cut out mid-sentence and never return. That's the level of intrigue here. Some researchers argue it could have been a natural phenomenon, like hydrogen gas swirling around a distant star, or even the reflection of a human-made satellite off a passing comet. But none of these explanations fully account for the signal's unique characteristics. The frequency it used, known as the water hole, is eerily quiet in the cosmic noise, a deliberate channel, some say, where advanced civilizations might broadcast to be heard. The lack of a repeat signal only deepens the mystery. If it was a natural event, why haven't we detected anything like it since? If it was artificial, why hasn't anyone or anything spoken up again? The silence is deafening, leaving us to wonder, was this a cosmic one-off, a fleeting echo of something unimaginable, or did we intercept a message never meant for us? Either way, the wow signal is a humbling reminder that the universe is full of voices we're only beginning to hear, and some, perhaps, we may never understand. If the wow signal left us questioning whether we're alone in the cosmos, dark matter presents an even more humbling puzzle, one that forces us to admit we might not even understand the basic scaffolding of the universe itself. Picture this: every star, every planet, every speck of dust we've ever observed makes up less than 5% of the universe's total mass. The rest, a mystery wrapped in shadows. 27% of the cosmos is made of something we can't see, can't touch, and can only detect by the way it tugs on the fabric of reality itself. It's like watching marionettes dance and realizing there must be invisible strings, except in this case, the puppets are entire galaxies and the strings are forces we've yet to name. The evidence for dark matter is everywhere once you know where to look. Galaxies spin so fast that their outer stars should be flung into the void, yet something unseen clings to them, a gravitational glue holding everything together. Light from distant galaxies bends as if passing through invisible lenses, warping space in ways that ordinary matter can't explain. Even the way galaxies cluster together, forming vast cosmic webs, points to the presence of mass we simply can't account for. The unsettling truth: what we call the universe might just be the tip of an iceberg, with dark matter as the hidden bulk lurking beneath. So what could it be? The leading theory suggests dark matter is made of particles unlike anything in our current physics playbook, particles that don't interact with light or ordinary matter, passing through our world like ghosts. Experiments deep underground and in colossal machines like the Large Hadron Collider hunt for these phantom particles, hoping to catch even a whisper of their existence. But after decades of searching, not a single definitive trace has been found. That silence has led some scientists to propose an even wilder idea. Maybe dark matter isn't missing matter at all. Maybe gravity itself works differently on cosmic scales, bending the rules in ways Einstein never predicted. The implications are staggering. If dark matter is real but invisible, it means we're surrounded by an entire shadow universe, its structures and rhythms humming silently alongside our own. But if it's an illusion, a sign that our grasp of gravity is flawed, then everything we know about the cosmos might need rewriting. Either way, dark matter isn't just a gap in our knowledge. It's a chasm, reminding us that the universe is far stranger, far more mysterious than we've dared to imagine. And until we solve it, we're left staring at the night sky, haunted by the question, what else is out there, unseen and unknown? Fast radio bursts are like the universe playing a cosmic game of peekaboo, blinding flashes of energy that appear out of nowhere, vanish in milliseconds, and leave scientists scrambling for answers. Imagine a pulse of radio waves so intense it outshines entire galaxies, carrying more energy than the sun emits in 80 years, all crammed into a flicker shorter than the blink of an eye. These bizarre signals, first detected in 2007, defy nearly every expectation. Some burst once and never repeat, like a firework lighting up the void. Others crackle back to life at random intervals, teasing astronomers with their unpredictability. What's particularly strange is how these bursts seem to follow no discernible pattern. Take FRB 121102, the first repeating fast radio burst ever discovered. It cycles through periods of frantic activity, unleashing dozens of bursts in hours, then falls silent for months. Then there's FRB 180916, which erupts roughly every 16 days like clockwork, a rare hint of order amid the chaos. This inconsistency has led to a zoo of theories. Could they be the death cries of neutron stars colliding in distant galaxies, the wakes of cosmic strings, hypothetical defects in spacetime? Or, as some have cautiously wondered, might they be traces of advanced civilizations harnessing unimaginable power? The plot thickened in 2020 when a fast radio burst was traced to a magnetar, a highly magnetic neutron star within our own galaxy. For a moment, it seemed the mystery was solved, until researchers realized most FRBs originate far beyond the Milky Way, and magnetars alone can't explain their staggering energy. Even more puzzling, some bursts show a strange twist in their radio waves, suggesting they've passed through extreme magnetic fields or dense cosmic plasma. It's as if each clue only deepens the enigma, forcing us to reconsider not just the bursts themselves, but the environments that produce them. Perhaps the most haunting question is this: if fast radio bursts are natural, why do they feel so engineered? The signals are concentrated in a narrow band of frequencies, almost as if optimized for transmission across interstellar space. And their brightness implies they're not just cosmic accidents, but focused emissions like a lighthouse beam sweeping past Earth. Whether the answer lies in exotic astrophysics or something even more profound, one thing's certain: fast radio bursts are a reminder that the universe still holds phenomena beyond our wildest imagination. And with every new detection, we're left wondering, what's next? Hidden behind the dense veil of stars and dust in our own Milky Way lies an enigma so massive, it's tugging entire galaxies toward it like a cosmic siren. Scientists call it the Great Attractor, a gravitational anomaly so powerful, it's pulling thousands of galaxies, including our own, at speeds of 14 million miles per hour. Picture a river of galaxies, all flowing toward some unseen waterfall in the void. This isn't just a gentle drift, it's a full-scale celestial migration, and for decades its cause remained hidden, obscured by the very galaxy we call home. The first clues emerged in the 1970s when astronomers noticed something peculiar. Galaxies in our cosmic neighborhood weren't just moving apart as the universe expanded, they were also drifting sideways as if drawn by some invisible hand. The direction, a patch of sky in the constellation Centaurus, buried behind the thickest part of the Milky Way's disk. It's like trying to peer through a sandstorm to find the source of a distant roar. Early observations suggested a concentration of mass, perhaps a supercluster of galaxies, but the numbers didn't add up. The gravitational pull was far stronger than anything visible could explain. Then came the game changer: infrared and radio telescopes capable of seeing through the Milky Way's dust. What they revealed was even more astonishing. The Great Attractor isn't just a single cluster. It's part of an even larger structure called the Laniakea supercluster, a web of galaxies spanning 500 million light-years. At its heart lies the Norma cluster, a dense gathering of galaxies with enough mass to account for some but not all of the attraction, the rest still a mystery. Some theorize a supermassive black hole lurks there, far larger than anything we've seen. Others suggest vast clouds of dark matter or even exotic physics we've yet to discover. What makes the Great Attractor so unsettling isn't just its hidden nature, it's the possibility that we might be missing something fundamental about how gravity works on the grandest scales. Could there be structures in the universe so immense, so alien, that they redefine our understanding of cosmic architecture? Upcoming telescopes like the James Webb Space Telescope and next-generation radio arrays aim to strip away the Milky Way's curtain once and for all. Until then, the Great Attractor remains a humbling reminder. Even as we map the cosmos, some forces are still pulling the strings from the shadows. In the constellation Cygnus, about 1,400 light-years from Earth, a star behaves like nothing else we've ever seen. Known as Tabby's star, officially KIC 8462852, it flickers and fades in ways that defy all conventional explanations. Most stars exhibit tiny, regular dips in brightness when planets pass in front of them. But Tabby's star doesn't play by those rules. Its light dims erratically, sometimes by as much as 22%, as if something colossal and misshapen is drifting across its face. The pattern is so bizarre that when astronomers first spotted it in data from the Kepler Space Telescope, they were left grasping for answers. The leading natural explanation points to swarms of giant comets, hundreds of times larger than anything in our solar system, orbiting the star in tight, chaotic formations. As these icy fragments break apart or collide, they could cast irregular shadows across the star's light. But there's a problem. Even the most extreme comet scenarios struggle to explain the sheer scale and irregularity of the dimming. Some dips last for days, others for weeks, with no predictable rhythm. Then there's the star's long-term fading. Over the past century, Tabby's star has grown steadily dimmer, losing nearly 20% of its brightness in a slow, inexplicable decline. This is where things get speculative and thrilling. In 2015, astronomer Jason Wright floated a radical idea. What if the dimming isn't natural at all? What if we're seeing the shadows of a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harness a star's energy? The concept isn't as far-fetched as it sounds. A Type 2 civilization on the Kardashev scale, a hypothetical society capable of stellar engineering, might construct vast arrays of solar collectors around their star, blocking light in uneven patterns. While Wright himself stressed this was a last resort explanation, the mere possibility ignited imaginations worldwide. Yet every attempt to confirm or rule out the megastructure theory has only deepened the mystery. Radio telescopes have detected no artificial signals from the star's direction. Infrared observations found no excess heat that would hint at energy harvesting technology. And recent studies suggest fine dust, not solid megastructures, is likely causing the dimming. But even dust can't fully explain the star's behavior. Why does it dim in such sharp, jagged drops instead of smooth curves? Why does it brighten again in unpredictable bursts? Tabby's star is more than an astronomical oddity. It's a cosmic Rorschach test. For some, it's a cautionary tale about jumping to extraordinary conclusions. For others, it's proof that the universe still holds phenomena so strange, they challenge us to rethink the boundaries of science. Whether the answer lies in swarms of comets, undiscovered physics, or something beyond our current understanding, one thing is certain: this star refuses to be easily explained. And in that refusal, it offers a tantalizing glimpse into just how much we still have left to discover. The universe is unimaginably vast, trillions of galaxies, each brimming with billions of stars, countless planets. Statistically, life should be everywhere, and yet when we listen, when we search, all we hear is silence. This eerie contradiction, the chasm between expectation and reality, is the Fermi paradox, a puzzle so profound it forces us to confront uncomfortable questions about intelligence, survival, and our own cosmic significance. Enrico Fermi first voiced the question in 1950. If civilizations rise across the cosmos, where is everybody? Even at modest speeds, a spacefaring species could colonize the Milky Way in a few million years, a blink in cosmic time. The fact that we see no signs of these galactic neighbors suggests something is terribly wrong. Maybe civilizations inevitably destroy themselves, snuffed out by war, climate collapse, or runaway technology. Or perhaps they're hiding, avoiding detection for reasons we can't yet fathom. One of the darker answers is the Great Filter theory, the idea that some nearly insurmountable challenge wipes out intelligent life before it can spread. The terrifying possibility: we haven't hit that filter yet, but not all explanations are so grim. Maybe we're simply looking in the wrong way, like ants trying to spot airplanes by staring at the ground. Advanced civilizations might communicate through neutrinos or gravitational waves, channels we're only beginning to explore. Others could be surrounded by Dyson swarms, their stars dimmed into near invisibility. There's even the zoo hypothesis, the notion that alien societies deliberately avoid contact, observing us like some cosmic nature preserve until we reach a technological maturity they deem worthy. Then there's the possibility that intelligence itself is rarer than we think. Complex life might require a series of miracles, a stable star, a protective moon, plate tectonics aligning perfectly across billions of years. Or perhaps civilizations inevitably turn inward, abandoning interstellar exploration for virtual realities indistinguishable from magic. The silence might not mean we're alone. It might mean we're early or late or simply missing the signs. The Fermi paradox isn't just about aliens, it's a mirror. However we resolve it, the answer will reveal something fundamental about life, technology, and the fragility of intelligence. And until we know for sure, the stars will keep their secrets, leaving us to wonder, is the universe a bustling metropolis, or are we shouting into an empty abyss? The longer the silence lasts, the heavier that question becomes. Einstein called it spooky action at a distance, a phenomenon so strange it made even the father of relativity deeply uneasy. Quantum entanglement, the bizarre link between particles that instantly mirrors changes across any distance, defies everything we know about space and time. Picture two coins flipped simultaneously on opposite sides of the galaxy, somehow landing on the same face every single time. Now imagine they're not just correlated, but fundamentally bound in a way that measuring one immediately determines the state of the other. No signal, no delay, just an instantaneous connection that ignores the cosmic speed limit of light. This isn't science fiction, it's laboratory-confirmed reality, and it shakes the very foundations of physics. The roots of this mystery stretch back to the 1930s, when Einstein and his colleagues highlighted entanglement as a glaring flaw in quantum theory, arguing nature couldn't possibly work this way. Yet experiment after experiment proved them wrong. In labs worldwide, scientists have entangled particles, photons, electrons, even tiny diamonds, and watched as altering one instantly influenced its partner, whether separated by meters or hundreds of kilometers. The most mind-bending part, this connection isn't just fast, it's truly instantaneous, operating outside the constraints of spacetime itself. Einstein's spookiness isn't a bug in the system, it's a fundamental feature of the universe. So what's really happening here? One interpretation suggests entanglement reveals a hidden layer of reality where particles aren't truly separate to begin with. Think of the universe as a vast, interconnected hologram where what we perceive as distant objects are just projections of deeper, underlying unity. Others propose even wilder ideas, like parallel universes brushing against our own entangled particles, could be interacting through dimensions we can't see. Then there's the pilot wave theory, which argues particles are guided by invisible forces, like leaves swept along by an unseen river. Yet for all the theories, no one can fully explain how entanglement works, only that it does. Practical applications already exist, from ultra-secure quantum cryptography to the fledgling field of quantum computing, where entangled bits perform calculations no classical machine could match. But the philosophical implications loom larger. If particles can communicate faster than light, does causality, the idea that cause must precede effect, still hold? Could entanglement hint at a universe where time and space are illusions, and all things are somehow entwined at a level we've yet to comprehend? The enigma cuts to the heart of reality itself. Either the universe is far stranger than we've imagined, or our understanding of its basic rules is profoundly incomplete. Quantum entanglement doesn't just challenge Einstein. It forces us to confront the unsettling possibility that the cosmos operates on principles beyond our current grasp. And with every experiment, the mystery only deepens, leaving us to wonder what other secrets might be lurking in the quantum shadows. When NASA Pioneer 10 and 11 spacecraft ventured beyond the edges of our solar system, they carried with them humanity's hopes and an unsolved mystery that would perplex scientists for decades. These intrepid probes, launched in the early 1970s, were expected to coast smoothly through the void, their trajectories governed by the familiar pull of gravity. But something was off. As they drifted farther from the sun, both Pioneers began slowing down ever so slightly, as if an invisible hand were tugging them backward. The discrepancy was tiny, less than a billionth of the acceleration you'd feel from Earth's gravity. But in the precise world of orbital mechanics, even the smallest anomaly can hint at something profound. At first, researchers assumed mundane explanations. Maybe residual fuel was leaking from the probe's thrusters, or heat radiating unevenly from their power sources was nudging them off course. Yet meticulous calculations ruled these out. The slowing was too consistent, too uniform across both spacecraft, separated by billions of miles. The effect became known as the Pioneer Anomaly, and for years it lingered at the edges of physics like a ghost in the equations. Some dared to wonder, could this be a sign of new physics, a crack in Einstein's theory of gravity itself? The implications were staggering. If the anomaly stemmed from an unknown gravitational quirk, it might mean our understanding of mass and acceleration was incomplete, a revelation that could upend everything from spacecraft navigation to cosmology. One radical theory suggested the existence of modified Newtonian dynamics, or MUND, a tweak to gravity's rules that could explain the Pioneer's behavior without invoking dark matter. Others speculated about unseen matter lurking in the outer solar system, or even exotic forces tied to the fabric of spacetime. Then, in 2012, painstaking analysis finally cracked the case, or so it seemed. A team of researchers concluded that heat from the Pioneer's radioactive power sources, bouncing asymmetrically off their antennae, was generating just enough recoil to account for the anomaly. Case closed, not quite. While this explanation fits much of the data, a handful of scientists still argue the heat theory doesn't fully reconcile all the numbers. The debate lingers, a reminder that even in the era of precision spaceflight, the universe still holds surprises. What makes the Pioneer Anomaly so compelling isn't just the mystery itself, it's the humility it demands. Here were two human-made objects hurled into the unknown, teaching us that even the laws we consider absolute might have unread footnotes. Whether the final answer lies in thermal physics, unseen matter, or something even stranger, one truth remains: every probe we send into the dark isn't just exploring space. It's testing the boundaries of our understanding, one anomalous tick of data at a time. The cosmic microwave background, the afterglow of the Big Bang, should be the ultimate testament to a universe born uniform and symmetric, a vast expanse with no preferred direction. Yet when scientists mapped its faint whispers across the sky, they stumbled upon something that shouldn't exist: an eerie alignment, a cosmic tilt, as if the universe itself had quietly chosen a favorite axis. Dubbed the axis of evil by researchers half-jokingly, this peculiar pattern defies one of cosmology's most sacred principles, the idea that the universe on large scales looks the same in all directions. What makes this axis so unsettling is how it weaves through multiple layers of cosmic data. The temperature fluctuations in the microwave background aren't randomly scattered. They show a subtle but statistically significant preference along a specific plane, almost like a hidden equator running through space. Even stranger, this alignment seems to match up with the plane of our solar system and the orientation of distant quasars, connections that stretch across billions of light years. The odds of this happening by chance, less than 1 in 10,000. Either we're witnessing the universe's most improbable coincidence, or there's a flaw in our fundamental assumptions about reality. Some cosmologists argue it's just a quirk in the data, an artifact of measurement errors or incomplete sky surveys. Others propose more radical explanations. Could the axis of evil be a fossil imprint, a scar left by something that existed before the Big Bang? theories like conformal cyclic cosmology suggest our universe is just one in an endless chain, each cycle leaving faint traces in the next. If true, this axis might be a glimpse beyond the veil, a shadow of a previous cosmos bleeding into our own. Then there's the possibility of a multiverse. Our universe might be one bubble among countless others, and the axis reflects the gravitational tug of a neighboring bubble pressing against ours. But the most provocative idea, that the universe isn't just uneven, it might be fundamentally anisotropic, with physics itself varying depending on direction. This would upend Einstein's cosmological principle, the bedrock assumption that the universe is smooth and isotropic at large scales. If true, it would mean the laws we take for granted, gravity, the speed of light, even the behavior of atoms, could subtly change as you move through space. Imagine a compass that didn't point north but toward a region where time flows differently or where matter behaves in ways we've never seen. The axis of evil isn't just a mystery, it's a crisis in cosmology. Either we're misreading the universe's most ancient light, or we're standing at the edge of a paradigm shift, staring into a cosmic funhouse mirror that distorts everything we thought we knew. Upcoming missions like the European Space Agency's Euclid telescope aim to scrutinize the microwave background with unprecedented precision, hunting for clues that could confirm or dismantle this eerie alignment. Until then, the axis lingers, a silent challenge to our understanding of the cosmos, whispering that the universe might not be as random as we once believed. And if that's true, what other symmetries might be illusions waiting to unravel? Most planets orbit stars like dutiful children, tethered by gravity's unbreakable leash, but not all. Drifting through the void between stars, invisible to traditional telescopes, lurk the universe's loners, rogue planets. These nomadic worlds, untethered from any solar system, wander the cosmic wilderness alone. Some were flung from their birthplaces by gravitational chaos. Others may have formed in the frigid darkness of interstellar space, never knowing the warmth of a sun. And here's the haunting part: these dark, frozen worlds might not be as lifeless as they seem. Imagine a planet untethered from its star, a frozen wasteland where temperatures hover near absolute zero. Yet beneath an icy crust, tidal forces from a distant galaxy's pull or the slow decay of radioactive elements could keep a subsurface ocean liquid. On Earth, we've found life thriving in the most hostile places: volcanic vents, Antarctic ice, even the crushing depths of the Mariana Trench. If life can cling to existence here, why not in the abyss of a rogue world's hidden sea? Some researchers speculate these wandering planets could outnumber stars in our galaxy by a staggering margin, turning the Milky Way into a shadowy archipelago of potential habitability. Detecting these cosmic drifters is like searching for a black cat in a pitch-black room unless it passes directly in front of a distant star, briefly warping the starlight with its gravity. We'd never know it was there. That's how we've found the few confirmed rogue planets so far, like the Jupiter-sized object ominously named CFBD SIR 2149-0403. But smaller, Earth-sized wanderers, they're virtually invisible to current technology. That's about to change. Upcoming telescopes like the Nancy Grace Roman Space Telescope will hunt for these dark nomads using microlensing, potentially revealing thousands, if not millions, of them lurking in the galactic shadows. The implications are profound. If rogue planets turn out to be common, they could rewrite our understanding of planetary formation. Maybe violent collisions and gravitational ejections are more frequent than we thought, scattering worlds like shrapnel across the cosmos. Or perhaps these free-floating planets formed solo from collapsing gas clouds, bypassing the need for a star entirely. Either way, their existence forces us to reconsider what makes a planet a planet. But the most tantalizing question remains: could life exist in such isolation? Without sunlight, any organisms would rely on chemical energy or geothermal heat, a scenario not unlike Earth's deep-sea extremophiles. Some rogue planets might even retain thick hydrogen atmospheres, trapping enough warmth for liquid water on their surfaces. If life thrives there, it would prove that the ingredients for biology aren't confined to the cozy orbits of stars. They could be everywhere, adrift in the dark. Rogue planets are the universe's silent rebels, defying our expectations at every turn. They challenge us to imagine life in the most desolate corners of space and remind us just how little we know about the cosmic wilderness beyond our solar neighborhood. And as our telescopes grow sharper, these shadowy wanderers might just reveal that the galaxy is far stranger and more alive than we ever dared to dream. High above Earth, drifting silently through the void, an object whispers secrets we still can't decipher. The so-called Black Knight satellite, part myth, part mystery, has fueled conspiracy theories for decades. Some claim it's an ancient alien probe orbiting our planet for thousands of years, watching and waiting. Others insist it's just a piece of space junk, a forgotten remnant of human exploration. But the line between fact and folklore blurs whenever new details surface, leaving us to wonder what really lurks in those grainy images and cryptic radio signals. The legend began in the 1950s when newspapers reported strange echoes picked up by early radar systems, unexplained pings that seemed to originate from something orbiting Earth. Then, in 1960, a magazine article described a dark satellite of unknown origin, sparking wild speculation. The story snowballed when astronaut Gordon Kuiper allegedly sighted a mysterious object during his Mercury mission, though official records later attributed it to a faulty instrument panel. But the most tantalizing piece of evidence came from none other than Nikola Tesla, who in 1899 claimed to have intercepted peculiar radio signals, rhythmic pulses he believed might be attempts at interstellar communication. Could these have been transmissions from the Black Knight? Scientists have offered mundane explanations. The infamous satellite photographed during a 1998 space shuttle mission. Most likely a thermal blanket lost during a spacewalk. The eerie radio signals, natural phenomena or human-made interference. Even the orbital mechanics don't add up. An object as old as the legends suggest would have decayed and burned up in the atmosphere long ago. Yet, skeptics point to inconsistencies. Why do some images show a symmetrical, almost engineered structure? And what about those fleeting radio bursts still untraceable to any known source? Perhaps the most compelling aspect of the Black Knight isn't its existence, it's the cultural footprint it's left behind. From declassified government documents hinting at unexplained orbital objects to amateur astronomers capturing odd flashes in the night sky, the myth persists because it taps into a deeper question: are we being watched? Even if the Black Knight is just a collage of misidentified debris and coincidences, it reminds us how little we truly know about the space right outside our doorstep. With modern satellite tracking and advanced telescopes, we've mapped countless objects in Earth's orbit, but every so often, something slips through the cracks, an unregistered blip, an anomalous signal. Whether the Black Knight is a cosmic prankster, a glitch in our data, or something far stranger, one thing's certain: the universe loves a good mystery. And until we have incontrovertible proof, the legend will keep orbiting right alongside our curiosity. There's a place in the universe so empty, so unsettlingly vacant, that astronomers call it the Great Nothing. Nestled in the constellation Bootes lies a void so vast it defies comprehension, a spherical desert of darkness stretching 330 million light-years across, where galaxies should be crowding the sky, but instead there's almost nothing. Picture this: if you dropped the Milky Way into the Bootes void, the nearest galaxy would be so far away, our night sky would appear virtually black, devoid of neighboring stars. This isn't just a quiet corner of space, it's a cosmic anomaly so extreme. It forces us to question everything we know about how the universe structures itself. What makes the Bootes void so baffling isn't just its size. It's the sheer improbability of its existence. According to our best models of galaxy formation, matter should be distributed relatively evenly across the cosmos, with clusters and filaments forming a cosmic web. Voids are expected, yes, but none this colossal. The Boots void isn't just a gap, it's a staggering abyss containing roughly 60 known galaxies where there should be thousands. To put that in perspective, a region this size should host around 2,000 galaxies. Instead, it's a ghost town. The few galaxies that do cling to life here are isolated, scattered like lone survivors in an endless wasteland. How did this happen? Did something sweep this region clean, or was it born empty? Some theorists suggest the void might be the result of a perfect storm, an area where, by sheer chance, matter was unusually sparse during the universe's early expansion. Others propose a more unsettling idea. What if the void isn't empty at all? Could it be filled with something we can't see, like an ocean of dark energy pushing galaxies apart, or a concentration of dark matter so dense it warps the space around it into an invisibility cloak? There's even speculation, albeit controversial, that the Boots void could be evidence of a collision between our universe and another bubble in the multiverse, a cosmic bruise left behind by an unimaginable collision. Then there's the eerie possibility that we're missing something fundamental about how voids evolve. Recent simulations show that while the Boots void is extreme, it might not be impossible, just wildly improbable, like rolling a die 1,000,000 times and getting the same number every time. If that's the case, does its existence hint at flaws in our models? Or is it simply a reminder that the universe, for all its patterns, still holds room for the inexplicable? The Boots void doesn't just challenge science, it dares us to rethink our place in the cosmos. If regions like this exist, how many others might lurk beyond our sight? And what does that mean for life? Could galaxies stranded in the void, cut off from the cosmic web, become islands of solitude where intelligence flickers in the dark, unaware that anything else exists? The questions pile up faster than answers, leaving us humbled by the scale of our ignorance. For now, the Boots void remains an enigma, a silent monument to the universe's capacity for mystery. As telescopes grow more powerful, probing deeper into its shadows, we might yet uncover clues hidden in its emptiness. Until then, it stands as a haunting reminder. Even in a universe teeming with light and life, there are places where the rules seem to bend, and where our understanding hits a wall of perfect, impenetrable dark. The idea of an engine that generates thrust without fuel sounds like pure science fiction, a magic trick that defies the most fundamental laws of physics. Yet, for over 2 decades, the M drive has stubbornly refused to disappear from scientific discourse, lingering in the gray area between groundbreaking discovery and persistent experimental error. At its core, this controversial device is deceptively simple: a tapered, sealed metal chamber that, when filled with microwaves, allegedly produces a tiny but measurable push without expelling any propellant. No chemical explosions, no ionized particles streaming out the back, just an unexplained nudge forward that shouldn't exist according to Newton's third law. When British engineer Roger Scheuer first proposed the M drive in the early 2000s, the scientific community met the idea with outright dismissal. After all, the concept seemed to violate the conservation of momentum, a cornerstone of classical physics. If the M drive worked as claimed, it would be akin to sitting inside a car and pushing on the dashboard to make the vehicle move, a clear impossibility. But then something unexpected happened. Independent research teams, including a group at NASA Eagleworks Laboratory, began reporting anomalous thrust measurements in their own tests. The numbers were minuscule, often just a few micronewtons, but they were consistent enough to raise eyebrows. Even the most rigorous experiments couldn't entirely rule out the effect, leaving a tantalizing question. Was this a glitch in the equipment, or had we stumbled upon a loophole in the universe's rulebook? The implications are dizzying. A working M drive could revolutionize space travel, enabling spacecraft to accelerate indefinitely without carrying massive fuel reserves. Missions to Mars could be cut from months to weeks, and interstellar probes might reach neighboring stars within human lifetimes. But before we rewrite the textbooks, there's a mountain of skepticism to address. Critics point out that the measured thrust could be the result of thermal expansion, electromagnetic interference, or even subtle air currents inside vacuum chambers. Some argue the effect is simply too small to distinguish from noise in the data. And then there's the deeper philosophical hurdle. If the M drive works, what does that mean for our understanding of physics? Could it hint at hidden dimensions, quantum vacuum fluctuations, or some exotic interaction we've yet to comprehend? The M drive story is far from over. In 2021, a team at the University of Dresden conducted the most precise test to date, using a super-sensitive torsion balance to measure thrust. Their conclusion: the effect was likely caused by external magnetic fields interacting with the device's wiring, a plausible, if disappointing, explanation. Yet even this hasn't fully extinguished the debate. Scheuer and other proponents argue the Dresden experiment didn't replicate the exact conditions of earlier tests, leaving room for doubt. Meanwhile, private companies and international researchers continue tinkering with variations of the design, searching for that elusive spark of validity. What makes the M drive so captivating isn't just the technical controversy, it's what it represents. Humanity's hunger for the impossible, our willingness to chase anomalies even when they defy conventional wisdom. Whether the M drive ultimately joins cold fusion in the graveyard of tantalizing but unproven technologies or becomes the key to unlocking the stars, its legacy is already cemented. It's a reminder that science at its best thrives on the edge of the unknown, where the line between breakthrough and blunder is often vanishingly thin. And until we know for sure, the M drive lingers as a ghost in the machine of physics, whispering a question we can't yet answer. What if, just beyond Neptune, where the sun's light fades to a feeble glimmer, the solar system's outer reaches hold a mystery as stark as it is unexplained: the Kuiper cliff? This isn't some dramatic drop-off into a cosmic abyss, but something far stranger. A sudden, unnatural thinning of icy objects in the Kuiper belt, as if an invisible line were drawn across space. One moment you're counting hundreds of frozen worlds, plutonos, dwarf planets, and scattered debris, and the next the population plummets to near zero. It's like walking through a bustling city only to stumble upon a deserted district, its streets eerily empty. The question isn't just why this happens, it's what colossal force could have swept this region clean without leaving a trace. The leading theory points to a phantom planet, a hidden giant lurking in the darkness. Dubbed Planet 9 by some researchers, this hypothetical world would be 5 to 10 times Earth's mass, orbiting so far out that a single year could last 20,000 Earth years. Its gravitational pull, the thinking goes, could have yanked Kuiper belt objects into clustered, tilted orbits, or even hurled them into the abyss beyond the cliff. But here's the catch: no one's actually seen this planet. Its existence is inferred from the oddball paths of a handful of distant objects, their orbits tilted like misaligned clock gears. If it's out there, why hasn't our most powerful telescope spotted it? The answer might lie in its unimaginable distance, so far that the sun would appear as just another star in its sky, reflecting almost no light for us to catch. Yet not everyone's convinced. Some argue the Kuiper cliff could be a relic of the solar system's violent infancy. Picture this: 4.5 billion years ago, as the planets took shape, Jupiter and Saturn's gravitational tug of war might have slingshotted Neptune outward, scattering icy bodies like cosmic shrapnel. In this scenario, the cliff marks the edge of Neptune's migration, a frozen shoreline where the tidal pull of our solar system's formation finally ebbed. Others propose an even wilder idea, that the cliff is evidence of a long-lost sibling, a fifth giant planet ejected in the chaos of the early solar system, could have dragged countless objects with it as it tumbled into interstellar space. The void we see today, the ghostly imprint of that ancient cataclysm, but the plot thickens. Recent surveys have uncovered a handful of objects beyond the cliff, drifting in orbits that defy both the Planet 9 and migration theories. These lonely outliers, like the dwarf planet Sedna, loop the Sun in bizarre, elongated paths that shouldn't exist if Neptune's gravity were the only sculptor. Could they be the smoking gun for an undiscovered world, or do they hint at something even weirder, like the gravitational fingerprint of a passing star from billions of years ago? The more we study these distant wanderers, the clearer it becomes. The Kuiper cliff isn't just a boundary. It's a puzzle box layered with clues about forces that shaped our cosmic neighborhood in ways we're only beginning to grasp. What makes this mystery so compelling is the sheer scale of what we don't know. The Kuiper belt is the solar system's attic, stuffed with leftovers from its creation. Every odd orbit, every gap in the debris is a whisper from that ancient past, whether the answer lies in a hidden planet, a long-ago upheaval, or something beyond our current theories. One thing's certain: the outer solar system still holds secrets that could rewrite our understanding of home. And as telescopes grow sharper, probing deeper into the dark, we might finally learn whether that cliff is a footnote, or the edge of a story we've barely begun to read. The moment astronomers spotted Oumuamua streaking through our solar system in 2017, they knew it was no ordinary space rock. The first known visitor from another star system, this mysterious object tumbled past the Sun at blistering speeds, exhibiting traits that defied every expectation. Shaped like a flattened cigar, roughly a quarter-mile long but only a tenth as wide, it spun chaotically, reflecting sunlight in erratic bursts as if made of polished metal. Then came the real shocker. As it hurtled away from the Sun, something inexplicable happened. Instead of slowing down as gravity dictated, Oumuamua sped up as if propelled by an unseen force. At first, scientists scrambled to explain the acceleration with conventional physics. Maybe outgassing, the vaporization of ice into gas, was giving the object a gentle push, as often happens with comets. But here's the problem. Oumuamua showed no visible tail or coma, the telltale haze of a comet releasing gas. Telescopes scanned for traces of water or carbon dioxide, the usual suspects behind such bursts of motion, yet found nothing. The absence was deafening. Even stranger, the acceleration wasn't constant. It varied subtly, almost as if the object were maneuvering. This bizarre behavior led Harvard astronomer Avi Loeb to propose a radical theory. What if Oumuamua wasn't a natural object at all? Its unusual shape, the lack of outgassing, and the precise way it accelerated all seemed, to some, eerily artificial. Could it be a relic of alien technology, a solar sail catching the solar wind, or a derelict probe drifting between the stars? While most scientists remain skeptical, even the staunchest critics admit Oumuamua's oddities demand an explanation beyond textbook astronomy. Alternative theories abound. Perhaps it was a shard of a Pluto-like world, shattered by a distant cosmic collision, its surface rich in nitrogen ice that vaporized invisibly in the Sun's heat. Or maybe it was a fractal-like dust iceberg, a porous aggregate of interstellar material so light and fragile that sunlight alone could nudge it off course. Each hypothesis has holes. The nitrogen theory requires Oumuamua to be brighter than any known object in the outer solar system, while the dust model struggles to explain its sturdiness under the Sun's gravitational pull. What makes Oumuamua so haunting isn't just its strangeness, it's the fact we'll never get another look. By the time we spotted it, the object was already racing away, too distant for even our fastest probes to chase. Future telescopes might catch more interstellar visitors, but for now, Oumuamua remains a fleeting enigma, a cosmic passerby that left us with more questions than answers. Whether it was a bizarrely sculpted comet, a fragment of an alien world, or something beyond our imagination, one thing's certain: the universe is capable of crafting mysteries that leave even the brightest minds humbled. And if Oumuamua taught us anything, it's that the next strange visitor could arrive at any moment, ready to rewrite the rules all over again. The moon has always been Earth's silent companion, a barren world pocked by craters and bathed in dust. But buried in the rocks brought back by Apollo astronauts lies a clue that rewrites the lunar story. Traces of an ancient magnetic field, strong enough to rival Earth's. Here's the puzzle. Magnetic fields require churning molten metal cores, like the one powering our planet's protective shield. Yet today, the moon's core is small, cold, and geologically dead. So how did it once generate magnetism powerful enough to leave its mark on billion-year-old lunar samples? The answer might lie in a cataclysm so violent it reshaped the moon's very soul. For decades, scientists assumed the moon's magnetism was a fleeting side effect of its fiery birth. When a Mars-sized object smashed into early Earth, the debris coalesced into our moon, its core molten from the collision's heat. But models show that heat should have dissipated within a few 100 million years, yet the Apollo rocks reveal a magnetic field persisting for over 1 billion. Something kept that core churning far longer than physics predicts. One radical theory points to a second cosmic catastrophe. Imagine an asteroid the size of New Jersey slamming into the moon around 3 billion years ago, its impact so colossal it sent shockwaves through the lunar interior. Simulations suggest such an impact could have stirred the moon's core like a spoon in molten metal, reigniting convection currents and temporarily reviving its magnetic dynamo. But not everyone's convinced. Alternative explanations range from the moon's core crystallizing in uneven patches, creating turbulent swirls of liquid metal, to tidal forces from Earth stretching and squeezing the lunar interior like putty, generating internal friction and heat. Then there's the wild card: could the moon's mantle have played a role? Some minerals, when subjected to extreme pressure, can become electrically conductive. If the ancient moon's mantle was rich in these materials, its very rotation might have acted like a colossal generator, spinning a magnetic field into existence without a fully molten core. The implications stretch beyond lunar science. If impacts or tidal forces can jumpstart planetary magnetism, then icy moons like Europa or distant exoplanets might harbor magnetic fields under conditions we've never considered. It also forces us to rethink the moon's history as a static, lifeless rock. For eons, it may have pulsed with unseen energy, its core alive with currents we're only beginning to decipher. Each Apollo sample is a time capsule, preserving whispers of an era when the moon wasn't just a reflector of sunlight but a dynamic world with its own invisible shield, defying the quiet desolation we see today. What makes this mystery so compelling is its blend of violence and subtlety. The moon's magnetic past might hinge on the chaos of colossal impacts, yet its evidence survives in the faintest imprints on ancient rock. As new missions like NASA's Artemis program prepare to return to the lunar surface, scientists are hungry for fresh clues, especially from the moon's far side, where untouched rocks might hold the key to this billion-year enigma. Until then, the moon's magnetic ghost lingers, a reminder that even the closest worlds can keep staggering secrets hidden in plain sight. If the cosmic ballet of galaxies follows a script written by gravity, then something is missing from the stage. In 2008, astronomers studying the afterglow of the Big Bang stumbled upon a movement so strange, so unsettling, they called it the dark flow, a mysterious current dragging entire clusters of galaxies toward some unseen horizon at nearly 2 million miles per hour. These aren't just a few rogue galaxies breaking rank. We're talking about thousands of them, all streaming in the same direction like leaves caught in a cosmic river. The strangest part, there's nothing there to pull them. No supercluster, no black hole, not even a concentration of dark matter massive enough to explain this synchronized march into the void. The discovery came from NAS, a Wilkinson Microwave Anisotropy Probe, or WMAP, which mapped subtle temperature variations in the cosmic microwave background, the faint echo of the universe's birth. Researchers noticed these microwaves carried an imprint of motion. A Doppler shift revealing clusters were being tugged toward a single point in space far beyond the observable universe. At first, skeptics argued it might be an artifact of incomplete data or measurement errors. But when the Planck satellite confirmed the phenomenon years later, the scientific community had to confront a chilling possibility. Could the dark flow be evidence of something outside our universe exerting its gravitational influence? One leading theory suggests the flow is a remnant of the Big Bang's asymmetry. Imagine the infant universe as an unevenly inflated balloon, with some regions stretching faster than others. The dark flow might trace back to these primordial wrinkles, where space itself stretched in a preferred direction, leaving behind a gravitational wake that still tugs galaxies today. But others propose an even wilder idea. What if the pull comes from another universe entirely? In multiverse theories, where countless bubble universes float in a vast higher dimensional sea, gravity could leak between them like water seeping through a sponge. The dark flow might be our first glimpse of a neighboring cosmos, its mass warping the fabric of our reality from beyond the veil. Then there's the unsettling third option, that we're fundamentally wrong about gravity itself. Modified gravity theories suggest Einstein's equations might break down on cosmic scales, creating illusions of invisible forces where none exist. But even these adjustments struggle to explain the dark flow's sheer scale and coherence. Every explanation feels like grasping at cosmic straws, highlighting just how little we understand about the forces shaping the grandest structures in existence. What makes the dark flow so haunting isn't just the mystery, it's the implications. If it's proof of a multiverse, it rewrites our understanding of reality. If it's a relic of the Big Bang, it reveals just how imprinted our universe remains by its violent birth. And if it defies all known physics, then we're standing at the edge of a paradigm shift, staring into a darkness that might hold answers or deeper questions we're not yet equipped to ask. Until new telescopes or deeper observations shed light on this enigma, the dark flow remains a ghostly current, pulling not just galaxies but our curiosity toward the unknown. We think we know what the universe is made of: dark energy, dark matter, and the ordinary atoms that build everything from stars to smartphones. But here's the cosmic kicker: nearly half of that normal matter has gone missing. Not vanished, not transformed into something exotic, just hiding in plain sight, eluding every telescope and detector we've aimed at the sky. Scientists call this the missing Baryon problem, and it's one of astronomy's most humbling blind spots. Baryons, the particles that make up atoms, should be everywhere, yet when we tally up all the visible stars, galaxies, and gas clouds, we're left with a glaring deficit. Where did half the universe's building blocks go? The hunt for these phantom particles has led researchers to some of the hottest, most diffuse places in the cosmos. Imagine a spiderweb stretched across billions of light years, its filaments glowing faintly with gas so scorching it's invisible to optical telescopes. This is the cosmic web, the scaffolding of the universe, where theorists suspect the missing baryons lurk as ultra-hot plasma. At temperatures exceeding 1,000,000 degrees, this gas doesn't emit light. It absorbs it, leaving only the subtlest fingerprints in X-ray and ultraviolet spectra. In 2017, astronomers finally caught a break. By studying how distant quasars backlit these filaments, two independent teams detected the telltale signatures of oxygen ions, evidence that the missing matter was there all along, woven into the universe's vast, invisible threads. But even this discovery raises new questions. Why is the gas so blisteringly hot? Simulations suggest shock waves from collapsing galaxies and colliding superclusters could have heated it to extremes, but the energy required is staggering. Some propose active galactic nuclei, supermassive black holes spewing jets of energy pumped heat into the cosmic web like cosmic blowtorches. Others wonder if dark matter's gravitational pull played a role, stirring the gas into a frenzy as it funneled into filaments. And then there's the distribution puzzle. The gas isn't spread evenly. Some regions are dense enough to form faint, glowing halos around galaxies, while others stretch into near-perfect vacuums, challenging our models of how matter clumps together. The implications ripple far beyond accounting exercises. If half the universe's normal matter is tied up in these diffuse clouds, it means our galactic neighborhood might be swimming in undetectable hot gas, subtly influencing how galaxies spin and evolve. It also forces us to rethink how energy flows through the cosmos. The missing baryons aren't just hiding, they're active, trading heat and momentum in ways we're only beginning to map. Future telescopes like the European Space Agency's Athena X-ray Observatory aim to peel back the veil, capturing sharper images of these faint structures. Until then, the missing baryons stand as a reminder. Even the stuff we thought we understood can defy expectations, lurking in the shadows between the stars. Perhaps the most profound lesson here is one of perspective. For all our technological prowess, we're still learning to see the universe in its full complexity. The missing matter isn't lost, it's simply waiting for us to develop the tools, the patience, and the imagination to find it. And when we do, we might discover that the cosmos has been quietly rewriting its own rules, leaving traces for those willing to look beyond the light. In the constellation Monoceros, about 2,300 light-years from Earth, the Red Rectangle Nebula glows with an eerie symmetry that seems almost artificial. Most nebulae are chaotic clouds of gas and dust, sculpted by stellar winds into twisting tendrils or explosive bubbles. But not this one. Here, two cones of crimson light stretch outward from a central star, forming a near-perfect geometric shape that resembles an otherworldly stop sign. The structure is so precise, so unnervingly angular, that early images of it sparked whispers of cosmic engineering. But the real mystery isn't just its shape, it's that haunting red glow, deeper and more persistent than any known stellar phenomenon. At the heart of the nebula lies a dying star, HD 44179, expelling its outer layers in concentric waves. Conventional wisdom suggests such stars should create round, shell-like nebulae as their material drifts evenly into space. Yet somehow, this star's ejecta have collimated into two opposing cones, their edges razor-sharp against the blackness of space. The leading theory points to an unseen companion star, its gravity funneling the outflow into this bizarre geometry. But even that doesn't fully explain the nebula's most striking feature, its color. The deep red hue defies typical emission nebula spectra, which usually blaze with the greens and blues of ionized oxygen and hydrogen. Instead, the red rectangle's glow comes from something far stranger, a phenomenon called extended red emission, or ERE, where microscopic particles absorb ultraviolet light and re-emit it as a crimson haze. The culprit, a rare form of carbon-based dust, possibly arranged into crystalline structures or even complex organic molecules. Some researchers speculate these could be polycyclic aromatic hydrocarbons, PAHs, the same compounds found in soot and interstellar clouds. But here, they're behaving unlike anywhere else in the cosmos, clustering in ways that amplify their red glow to unprecedented levels. Then there's the wild card. Could these carbon structures be more complex than we think? A handful of scientists have dared to wonder if the red rectangle's dust might contain probiotic molecules, the kind that could seed life under the right conditions. It's a long shot, but the mere possibility adds another layer of intrigue to this already mesmerizing object. What makes the red rectangle so captivating isn't just its beauty, it's the way it challenges our assumptions about how stars die. Most planetary nebulae are fleeting, dissolving into the interstellar medium within tens of thousands of years. Yet this one has maintained its precise shape for millennia, as if frozen in time. Is its stability due to some unseen magnetic field, the influence of that hypothetical second star, or is there a yet undiscovered process at work, one that sculpts stellar debris into perfect geometric forms? As telescopes like the James Webb Space Telescope turn their gaze toward this cosmic oddity, we may finally uncover the secrets behind its crimson glow and razor-edged silhouette. Until then, the Red Rectangle stands as a testament to the universe's flair for the dramatic, a reminder that even in death, stars can create art more striking than anything we've imagined. And whether its mysteries are solved tomorrow or persist for centuries, one thing's certain: the cosmos has a way of painting outside the lines, leaving us to marvel at the strokes we don't yet understand. At the very edge of our observable universe, an impossible structure looms, a filament of galaxies so vast it defies the fundamental principles of cosmology. Known as the Hercules-Corona-Borealis Great Wall, this cosmic behemoth stretches an astonishing 10 billion light-years across, a web of galaxy clusters and superclusters arranged in a pattern that shouldn't exist. To put that in perspective, if you traveled at the speed of light, it would take you twice the age of Earth just to cross from one end to the other. And here's what truly rattles scientists: according to our best models of the universe, nothing should be that big. The problem lies in something called the cosmological principle, the bedrock assumption that matter should be distributed evenly across the cosmos when viewed at the grandest scales. Up until now, that principle held galaxies cluster into groups, which form superclusters, which in turn create a vast cosmic web. But even that web has limits. Based on the universe's age and expansion rate, theoretical physics places a hard cap on how large structures can grow, about 1.2 billion light-years. The Hercules-Corona-Borealis Great Wall smashes that limit by nearly an order of magnitude, stretching so far it essentially redraws the boundaries of what we thought was possible. So how did this cosmic titan come to be? One theory suggests it's a relic of the universe's infancy, a frozen ripple from the Big Bang's primordial chaos. Picture the early universe as a stormy sea, with quantum fluctuations generating waves of varying density. Most of these evened out as space expanded, but what if one of those waves was so vast, so deeply etched into the fabric of reality, that it persisted as a framework for matter to clump around? Another possibility is even more radical, that the Great Wall isn't a single structure at all, but a chance alignment of multiple superclusters, a trick of perspective magnified by the vast distances involved. But follow-up observations suggest the galaxy clusters within it are gravitationally bound, meaning they're not just randomly overlapping, they're truly connected. Then there's the unsettling implication: could the cosmological principle itself be flawed? If structures like this exist, it might mean the universe isn't as uniform as we've assumed. Some regions could be denser, emptier, or shaped by forces we haven't accounted for. This isn't just an academic debate, it strikes at the heart of how we measure cosmic expansion, dark energy's influence, even the ultimate fate of everything. Yet for all its enormity, the Great Wall remains frustratingly elusive. Its distance means we're seeing it as it was in the universe's youth, and much of it lies hidden behind foreground dust and stars. New telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope aim to peel back those layers, probing deeper into its structure and origins. Until then, the Hercules-Corona-Borealis Great Wall stands as both a monument and a challenge, a cosmic paradox written in galaxies, daring us to rethink the very rules of existence. TRAPPIST-1 should be a beacon of hope in the search for extraterrestrial life, a dim red dwarf star just 39 light-years away, orbited by 7 rocky worlds, 3 of which sit snugly in the habitable zone where liquid water could flow. It's the kind of system astronomers dream of, compact, Earth-sized, and tantalizingly close. Yet when we point our radio telescopes toward these planets, listening for even the faintest whisper of technology or biology, all we hear is silence. Not static, not ambiguous noise, just the void. The absence is so striking it raises a chilling question. In a universe teeming with planets, why does TRAPPIST-1 feel like a cosmic graveyard? One possibility is as simple as it is sobering. The system might be lethally inhospitable. Red dwarfs like TRAPPIST-1 are notorious for their volatility, prone to violent flares that can strip atmospheres and bathe planets in sterilizing radiation. Observations suggest the star erupted frequently in its youth, with flares hundreds of times more powerful than our Sun's. Any early oceans or nascent biospheres on its planets could have been boiled away eons ago, leaving behind airless rocks baking under an angry crimson sun. Even the so-called habitable zone might be a cruel misnomer. Without a thick atmosphere or a global magnetic field, these worlds could be as barren as Mercury, their surfaces scoured clean by eons of stellar tantrums. But silence doesn't always mean lifeless. Another explanation teases a more subtle mystery. What if life is there, but nothing like we expect? Earth's biosphere broadcasts its presence through oxygen-rich air, industrial radio waves, and the reflected glow of chlorophyll. But on a tidally locked world, where one face permanently bakes under the star's glare while the other freezes in eternal night, life might cling to twilight zones, communicating through chemical signals we wouldn't recognize as artificial. Or consider the possibility of subterranean ecosystems, thriving in oceans buried beneath miles of ice, their existence hidden from our telescopes. The universe isn't obligated to cater to our search parameters. Life could be flourishing in ways we're not equipped to detect. Then there's the eerie third option: we're not listening correctly. Our current searches focus on radio waves and optical signals, the technologies humanity has mastered. But an advanced civilization might have long abandoned these methods, communicating instead through quantum entanglement, neutrino beams, or other channels we're only beginning to theorize. Imagine ants trying to detect Wi-Fi. The signals are there, but the ants lack the context to understand them. TRAPPIST-1's silence might not be absence at all, just a mismatch between their technology and our assumptions. What makes this system so haunting isn't just the unanswered questions, it's the stark reminder of how little we know. TRAPPIST-1 could be a cautionary tale about the fragility of life in a violent cosmos, or it could be hiding a lesson about the diversity of intelligence. As next-generation telescopes like the James Webb Space Telescope study the atmospheres of these worlds, searching for traces of water or methane, we might finally get clues. Until then, those 7 silent planets orbit their faint star, keeping their secrets close, a puzzle as profound as the stars themselves. Science fiction has long imagined the edges of galaxies as uncharted frontiers, places where reality bends and unknown forces lurk. Star Trek famously depicted a galactic barrier, an impenetrable energy field that scrambled minds and warped spacetime. But what if fiction isn't entirely wrong? Some astrophysicists speculate that our own Milky Way might be surrounded by something just as enigmatic, a real-life boundary of energy, one that could rewrite our understanding of cosmic rays and the very limits of our galactic home. The clues lie in the behavior of ultra-high-energy cosmic rays particles racing through space at nearly the speed of light. These aren't your average interstellar travelers. They carry energies millions of times greater than anything produced in particle colliders on Earth. Yet something odd happens when we trace their paths backward. Instead of arriving uniformly from all directions, many seem to avoid the Milky Way's outer edges, as if repelled by an invisible shield. This isn't just a statistical fluke. Observatories like the Pierre-Auger Cosmic Ray Observatory have mapped this anomaly for years, finding a conspicuous drop-off in rays originating from the galactic perimeter. The question is, what's stopping them? One daring hypothesis suggests the galaxy is cocooned in a vast magnetic field, twisted into a chaotic web by the motion of charged particles and interstellar gas. At the edges, where the Milky Way's gravitational grip weakens, these fields could grow turbulent enough to deflect or even trap incoming cosmic rays, a natural barrier acting like a cosmic sieve. Supporting this idea are strange radio emissions detected from the galaxy's fringe, patterns that hint at dense, magnetized plasma churning in ways we don't fully understand. If confirmed, this wouldn't just be a boundary, it'd be a dynamic, energetic filter shaping what enters and exits our galactic neighborhood. Yet there's a catch. Magnetic fields alone might not explain the sheer violence of some cosmic rays that do breach the barrier. Enter an even wilder possibility: dark matter. If the galaxy's outer halo is dense with these invisible particles, their collisions could produce shockwaves of energy, creating secondary cosmic rays that muddy the data. Or perhaps the barrier isn't a fixed structure at all, but a ripple left by the Milky Way's motion through intergalactic space, like the bow wave of a ship plowing through water. Either way, the implications are staggering. If such a barrier exists, it could mean our galaxy isn't just floating passively in the void. It's actively interacting with it, encased in a cloak of forces we've only begun to detect. The mystery deepens when we consider distant galaxies. Observations of other spirals reveal similar radio halos and energy drop-offs at their edges, suggesting this phenomenon might be universal. But without a probe like Voyager, which took decades just to reach the heliosphere's edge, we're left to piece together clues from the cosmic rays and faint signals that trickle inward. Upcoming telescopes like the Square Kilometre Array could finally map these fringe fields in detail, revealing whether they're rigid walls or permeable membranes. What makes the galactic barrier theory so compelling isn't just the science, it's the philosophical shift it demands. For centuries, we've pictured galaxies as islands adrift in emptiness. But if they're wrapped in energetic frontiers, they might be more like castles with moats, their boundaries shaping the flow of cosmic traffic. Whether the answer lies in magnetism, dark matter, or something entirely unforeseen, one thing's clear: the edge of the galaxy isn't just a line on a map. It's a laboratory for the universe's most extreme physics, waiting to be decoded. And with every high-energy particle that defies expectations, the cosmos whispers a tantalizing challenge. There's more to the story than we've dared to imagine. The universe is expanding, that much we know, but how fast it's growing has become one of modern cosmology's most contentious puzzles. Meet the Hubble Tension, a glaring mismatch in the cosmic speedometer that's forced astronomers to question whether we've misunderstood the fabric of reality itself. On one side, we have meticulous measurements of nearby stars and supernova, all pointing to an expansion rate of about 73 kilometers per second per megaparsec. On the other, the afterglow of the Big Bang, the cosmic microwave background, suggests a slower, more sedate pace of 67. At first glance, the difference might seem trivial. But in the precise world of astrophysics, this 6-kilometer gap isn't just a rounding error. It's a crisis. Dive into the data and the tension only tightens. Take Cepheid variables, the universe's standard candles. These pulsating stars have predictable brightness cycles, allowing us to gauge distances to nearby galaxies with remarkable accuracy. Pair them with Type 1, a supernova stellar explosion so uniform they're used as cosmic mile markers, and the expansion rate comes into sharp focus. But when we compare these local measurements to the pristine snapshot of the early universe captured by the Planck satellite, the numbers refuse to align. It's as if the universe accelerated sometime after the Big Bang, breaking its own rules without leaving a note. This discrepancy has split the scientific community into warring camps. One faction insists the tension is a mundane calibration issue. Perhaps Cepheids are more finicky distance markers than we thought, or supernova aren't as uniform across cosmic time. Others point to gaps in our understanding of dark energy, the mysterious force driving the universe's expansion. What if dark energy isn't constant, as Einstein's cosmological constant suggests, but evolves over time, growing stronger or weaker in ways we haven't accounted for? Some theories propose it could interact with dark matter, creating a feedback loop that tweaks the expansion rate. Then there's the radical fringe, physicists flirting with the idea that we're missing an entirely new ingredient in the cosmic recipe. Could an exotic form of relic radiation from the early universe be subtly warping space-time? Or might gravity itself behave differently on the largest scales, bending the rules Einstein laid down over a century ago? The most tantalizing and unsettling possibility is that the Hubble tension isn't a problem to solve but a clue, a fingerprint of physics beyond the standard model. If true, it would mean the universe is playing a game we don't yet know the rules to. Upcoming telescopes like the Roman Space Telescope and next-generation cosmic microwave probes aim to settle the debate, scrutinizing the expansion rate with unprecedented precision. But until then, the Hubble tension remains a humbling reminder. Even the most fundamental constants of nature might not be as constant as we think. Whether the answer lies in overlooked errors, dark energy's secrets, or a seismic shift in physics, one thing's clear: the cosmos is still keeping score, and we're just beginning to learn how to read it. In the bizarre world of quantum physics, where particles pop in and out of existence and cats can be both dead and alive, there's a theoretical concept so strange it makes even seasoned physicists pause: the unparticle. Picture matter that doesn't behave like matter at all, substance that refuses to play by the rules of particles or waves. This isn't just another exotic particle waiting to be discovered. It's a radical reimagining of what matter could be, a form of existence that operates outside the frameworks we've used to explain reality for centuries. The idea first emerged in 2007 when physicist Howard Georgi proposed that at incredibly high energies, there could be unparticle stuff with no definite mass, no fixed position, and no predictable behavior. Unlike electrons or quarks, which follow strict quantum rules, unparticles would blur the line between particle and wave, existing in a fuzzy state that defies conventional measurement. Imagine throwing a pebble into a pond and watching the ripples spread, except in this case, the ripples don't diminish smoothly. They flicker unpredictably, sometimes vanishing entirely, other times flaring up stronger than before. That's the kind of chaos unparticles could bring to the subatomic realm. What makes this concept so electrifying isn't just its weirdness. It's the tantalizing possibility that unparticles might solve one of cosmology's biggest headaches: dark matter. If these elusive entities exist, they could account for the universe's missing mass without requiring new particles like WIMP or actions. Unlike traditional dark matter candidates, unparticles wouldn't clump neatly into halos around galaxies. Instead, their behavior would be fluid, almost ghostly, spreading unevenly through space in ways that might explain why dark matter's gravitational effects vary so mysteriously from one galaxy to another. Some researchers even speculate that unparticles could interact with ordinary matter through forces we've yet to discover, leaving faint traces in high-energy collider experiments or cosmic ray data. But the implications go far beyond dark matter. If unparticles are real, they could shatter the very foundations of quantum field theory, the mathematical framework that's ruled particle physics for decades. Suddenly, phenomena like quantum entanglement or the uncertainty principle might need revisiting, their familiar equations rewritten to accommodate this formless, fluctuating matter. It's like discovering that the periodic table has a hidden column, one filled with elements that refuse to bond or decay like anything we've seen. The ripple effects could extend into technology too. Unparticle-inspired materials might exhibit bizarre thermal or electrical properties, enabling breakthroughs in superconductivity or quantum computing, assuming we could harness something so inherently unpredictable. Of course, skepticism runs deep. Detecting unparticles would require spotting anomalies in particle collisions so subtle they could easily be mistaken for noise. Critics argue that the theory is too vague, a mathematical curiosity with no clear path to experimental confirmation. Yet history has shown that some of science's greatest leaps began as wild conjectures. Black holes, gravitational waves, even the Higgs boson were once dismissed as speculative fantasies. For now, the unparticle remains a specter in the equations, a tantalizing what-if hovering at the edge of discovery. Whether it's the key to dark matter, a gateway to new physics, or just a fascinating dead end, its very existence challenges us to ask, how much of the universe's rulebook have we truly read? And what other pages might be waiting, half erased in the cosmic shadows? If black holes are the universe's ultimate sinkholes, swallowing everything that crosses their event horizons, then white holes would be their cosmic counterparts, gushing fountains of matter and energy, erupting into existence with no way back inside. Theoretically, these bizarre objects are the exact inverse of black holes, governed by the same equations but playing the opposite role in spacetime. Where a black hole's gravity is so intense even light can't escape, a white hole repels everything, violently expelling material outward like an infinitely pressurized geyser. Nothing can enter, it's a one-way exit door from the universe's most mysterious depths. The idea stems straight from Einstein's theory of general relativity. When mathematician Karl Schwarzschild first solved Einstein's equations in 1916, his solutions described not just the warped spacetime around black holes, but also their hypothetical twins, regions where matter and energy burst forth from an impassable boundary. For decades, physicists dismissed white holes as mathematical curiosities, artifacts of the equations with no basis in reality. But in recent years, they've resurfaced as potential keys to some of cosmology's greatest puzzles. Take the black hole information paradox, which asks what happens to the information locked inside a black hole when it evaporates via Hawking radiation. If black holes transform into white holes at the end of their life cycles, spewing out their contents in a final, fiery eruption, that missing information might not be lost after all, just delayed, like a cosmic message in a bottle waiting to be uncorked. Then there's the tantalizing possibility that white holes could explain cosmic explosions of unimaginable scale. Some theorists speculate that certain ultra-high-energy gamma-ray bursts, flashes of light brighter than entire galaxies, might be white holes briefly flickering into existence. These wouldn't be permanent structures but fleeting events, the universe's way of balancing the books after a black hole's demise. Others go even further, suggesting white holes could be the birth cries of entirely new universes. In this mind-bending scenario, the matter erupting from a white hole doesn't re-enter our universe at all, but instead becomes the seed for a separate spacetime continuum, bubbling into existence like a droplet pinching off from a larger body of water. Yet for all their theoretical allure, white holes face one glaring problem: we've never seen one. No known astrophysical process explains how they could form naturally. Black holes collapse from dying stars or merge in violent collisions, but white holes would require conditions so extreme they border on the miraculous, like time reversing inside a black hole's core, or a singularity spontaneously uncollapsing. Even if they did exist, their very nature makes them spectacularly unstable. A white hole pumping matter into the universe would attract surrounding material, which upon contact could collapse the entire structure back into a black hole, snuffing it out in a cosmic paradox. Perhaps that's why some researchers argue white holes aren't objects at all, but moments, brief flashes of spacetime's flexibility, etched into the fabric of the universe like scars. Others propose they're hiding in plain sight, masquerading as distant quasars or the mysterious fast radio bursts that crackle across the cosmos. Until we spot one or devise experiments to test their existence, white holes remain locked in the realm of equations and imagination. But in a universe where black holes once seemed equally implausible, that might not be the final word. After all, the cosmos has a habit of outrunning our wildest theories, and if white holes are real, they wouldn't just solve paradoxes. They'd rewrite the story of how reality itself breathes, lives, and rebirths. From unexplained signals to invisible forces, these 25 cosmic mysteries are more than just scientific curiosities. They're humbling reminders of how much we still don't know. Every strange signal, every gravitational anomaly, every inexplicable structure in the void forces us to confront the limits of human understanding. The universe isn't just vast, it's teeming with phenomena that defy our textbooks, challenge our instruments, and spark debates that ripple through the scientific community. And that's the beauty of it. Discovery isn't a checklist to complete, it's an endless frontier, with each answer unveiling new questions even more baffling than the last. Think about it, a century ago, dark matter wasn't even a concept, fast radio bursts undreamed of. Now, these mysteries aren't just puzzles, they're invitations. Invitations to rethink physics, to build better telescopes, to venture deeper into the unknown. Whether it's the eerie silence of TRAPPIST-1 or the ghostly tug of the Great Attractor, these enigmas prove that the cosmos refuses to be boxed into our current frameworks. And that's exactly what makes science so thrilling. The moment we assume we've got it all figured out, the universe throws us a curveball, shattering complacency and reigniting curiosity. But here's the most exciting part. The next breakthrough could be just around the corner. A new telescope might capture an image that rewrites astronomy. A lab experiment could stumble upon a particle that cracks the dark matter code. Or perhaps an amateur astronomer scanning the night sky from their backyard will spot something so strange it sends researchers scrambling. The universe doesn't reveal its secrets on a schedule, it surprises us. So what's your favorite cosmic mystery? Is it the wow signal's tantalizing whisper, the great nothing's unsettling void, or something we didn't even cover today? Drop your thoughts in the comments. I'd love to hear which enigma keeps you up at night, staring at the stars and wondering. And if you're hungry for more deep dives into the unknown, don't forget to hit subscribe. Because one thing's certain, the cosmos isn't done keeping secrets, and we're just getting started on the journey to uncover them.